Okay, here we go with our recording. Today's lesson is on what are called limits. We haven't talked about those yet, and discontinuities. And the goal for today is for me to tie the stuff we did with numbers and polynomial synthetic substitution. Just writing one down. We're going to tie together materials like this with the pictures of the graphs we talked about yesterday. I'm going to work off of the notes for a while, and then I'm going to come back to the notes. And well, I shouldn't say that. I'm going to paraphrase the notes. You can write things down if you want. They'll be based on that. So let's forget for a minute about the polynomial long division. I'm going to bring it back in, or the polynomial substitution. And we're going to talk specifically about two types of discontinuities, two types. The first one being removable. And the second type being infinite discontinuities. Okay, so removable discontinuity is just one where if we have a function there is a hole in the graph. As a matter of fact, for this particular function, I could say that f of 3 is undefined. There is no value of this function of the graph at 3. Everywhere else there's a value, but at 3 there is no value. For the infinite discontinuity, there's still a break in the graph, but instead of being a hole, there might be an asymptote. And we might say that f of 3 is still undefined. There is no value for any of those graphs right there. Okay, so here's the new term we're going to talk about, and then we'll bring back in the info on the math part of it. We're going to talk about something called a limit. Write it down. A limit is a new math term we're going to talk about. And the limit doesn't actually have to do with the value. It's about where a graph heads as you approach a certain x value. So it's about talking about where the graph heads as you approach a certain x value. And I'm going to be careful with where I said where it heads. It's the y value it heads towards as you approach a certain x value. It's a little strange to think about. It doesn't really matter what happens when you get there. It's just kind of where it's heading to. Okay, so let's look at a graph of this to see if we can understand what's going on. I'm going to draw a new picture. Okay, so I've drawn myself a function, and I'm going to call this function f of x. First of all, are there any discontinuities in the graph? Where are they? Oop, can't see that, can I? There we go. Discontinuity, there is one at x equals 2. I'll put an arrow on it. Is there another one in the graph? Yes, there is. It's at x equals 3. X equals 3 is an infinite discontinuity. And x equals 2 is what's known as a removable discontinuity. It can be the discontinuity can be removed by filling in the dot. Okay, so what does this mean in terms of values of the graph? So I'm going to write down a couple of f values. F of 1. Oh, parentheses. F of 2. F of 3. F of 4. And F of 5. And these are going to be the values of the graphs at those particular spots. Let's take a look. The value of the graph at f of 1 is the height of the graph there. It's negative 1. Let's skip over to 4. The height of the graph at 4 is 2. And the height of the graph at 5 is -2. So these are values. But what's the value of the graph at 2? Well, there's no value there. There's a hole. So this graph is undefined. And f of 3, it is also undefined. They have no particular value there. Okay, so now we're going to do our new math. And I'm only introducing it today. Then we're going to do the algebraic part of it, which is what's called limits. Limits are just the value you head towards as you approach a certain number. So I'm going to start really simple. I'm going to show you the symbols for limits. I would write like this: the limit as x approaches 1 of f of x equals. That just says where does the height of the graph go as x approaches 1 from both sides. So if I look here, as I approach 1 from this side, I'm approaching a height of 1. As I approach, -1. As I approach 1 from this side, I also approach a height of -1. I'm approaching the same height from each side. So the limit of that function is equal to -1. It's actually really easy when a graph is continuous. It's just the value that you're heading towards. For example, if I did f of 4, the limit as x approaches 4, so this part is the x value. As I approach from this side, the height of the graph approaches 2. You can see actually it's a little bigger than 2. But it's getting closer and closer. The height's getting closer and closer to 2 as I get close. Here, right now the height's a little less than 2. As I get closer and closer, it approaches 2. So the limit equals 2. So now let's find the limit. I'm going to write these two off to the side because they're a little different. Let's do them in red here for this first one. Let's find the limit as x approaches 2 of f of x. So remember, f of 2 is undefined. There's no value there. But I'm not really concerned about the value itself. I'm looking at what happens as I get closer. So for example, here's the number 2. As I get closer to that x value, I'm going to start right here. I say right there the height is like 0.8, 0.9, 0.93, 0.99, 0.999. As I get really close to 2, the height of the graph looks like it's getting close to 1. That'll come from the other side. 1.5 is the height. 1.4, 1.3, 1.2, 1.1, 1.01, 1.001, 1.001. So I come from this side, the height is getting close to 1. I know there's no value there, but just tell me what happens if I get really, really close to it. The limit of that graph, the limit of the graph as x approaches 2 is equal to 1, because the height of the graph, as we get close to that spot, approaches 1. We don't care what happens when we get there, we just care what happens as we get close. So now let's take a look at the green one, which is number 3. Let's find the limit as x approaches 3 of f of x. Well, let's look at some heights here. Let's get close to 3, 2, 2.5, 3, 100, 150. As a matter of fact, as I get closer and closer to 3, the heights are going up, but they're not actually reaching any number. The same thing happens on the other side. If you've seen the movie Mean Girls, you know the answer to this question. For this function here, the limit does not exist. Meaning, as I get closer and closer to 3 from both sides, I'm not actually approaching any number. I'm heading off towards somewhere different. So from a mathematical perspective, the two things we talked about, for removable discontinuity, your function will have a limit. And for an infinite discontinuity, your function does not have a limit. It's all about the value you get close to as time goes by. Okay, so now today we're just going to move into the algebraic part of this, meaning we talked about what we talked about before. There's removable and infinite discontinuities. I have examples of 2 functions right here which we've worked on for the past couple days. One of them had a removable discontinuity, and one of them had an infinite discontinuity. The question is, how can we algebraically find those discontinuities by just using the math part of it? And it's pretty straightforward. We're going to do 2 things in this lesson. I'm going to do a video now that I'm going to continue on in a minute that shows you how to find them algebraically by computing what are called limits. Limits are just a little new tool we're going to add. Instead of saying f of x is equal to, we're going to find the limit as x approaches 3 of x cubed minus 5x squared plus 8x minus 6 over x minus 3. And we're going to do the same thing on this side. We're going to see if we're going to get any difference between the two. 8x minus 5 and x minus 3. For a small aside for a second, I don't want to overcomplicate what limits are. Limits are the value you approach as you head towards a certain number. Now the function is just smooth and continuous, like this one right here. There's no breaks in the graph. This is the graph of f of x equals x squared. Now f of 3 will be equal to 9. That's just the value of the graph. If I put it in, I would get that. When you're looking for limits, if you just put this number in for x, 3 squared equals 9. If you get a number back, that's the actual limit. So on smooth continuous functions, the value and the limit are exactly the same because I'm heading to the same location. Now let's talk about when a graph is not continuous, what happens. So we're going to go focus back on these two. And this is the only math piece we're going to look at for these problems. Hold on. So I think I got the focus here good. So to find limits of any functions, we literally just take the number we have and we put it into the equation. Okay? I'm going to start with this one right here. So we're going to limit as x approaches 3. I'll fill 3 into the top. 3 cubed minus 5, 3 squared plus 8 times 3 minus 6 over 3 minus 3. And guess what I would do to the other side? I do the exact same, the other equation for the exact same thing. Limit as x approaches 3 of 3 to the third minus 5, 3 squared plus 8 to the third minus 6 over 3 minus 3. There's something you should notice about both problems, is that the bottom of the problem is going to give me a 0. That just lets me know that these functions are discontinuous at that spot because the bottom of the graph is 0. Okay, so now if I were to pause this for a second, I'm going to go and find this number. Hold on. Okay, I fixed it for you. Okay, so if I did the math in the top part of this problem right here, I'm going to get 0 over 0, which is a special term we're going to talk about in a minute. On the other function, I'm actually going to end up with 1 over 0. Okay, if you get any number over 0, you are done. You know then that the limit does not exist. There's no limit to a function that ends up in this fraction form. And we can see by the picture that makes sense. 1 over 0 is like indeterminate. You can't find it, but it means we have an asymptote. We're going to have on our graph right there. But if we get 0 over 0, this is a special form. It's called indeterminate form. And it means we don't know what's going on here. So what I'm going to do is I'm going to pause. So basically, if we work on a problem and we put a number in and we get 1 over 0, any number over 0, we're done. It doesn't have a limit. The question is what's going to happen when we get this indeterminate form. We're going to come back in our second video and discuss that in a moment.